Hello everyone, welcome to the course on elliptic curve arithmetic. So here most of the products and standards that use this public key cryptography for encryption and digital signatures use RSA. So the key length for secure RSA use has increased over recent years, and this has put a heavier processing load on application using RSA. This burden has ramifications, especially for electronic commerce sites that conduct large numbers of secure transactions. A competing system challenges RSA, elliptic curve cryptography, that is ECC. ECC is showing up in the standardization efforts, including the IEEE P1363. This is a standard for public key cryptography. The principal attraction of ECC compared to RSA is that it appears to offer equal security for a far smaller key size, thereby reducing processing overhead. On the other hand, although the theory of ECC has been around for some time, it is only recently that products have begun to appear and that there has been sustained cryptanalytic interest in probing for weaknesses. The confidence level in ECC is not yet as high as that in RSA. So this error correction codes is fundamentally more difficult to explain than either RSA or Diffie-Hellman, and a full mathematical description is beyond the scope. So here we'll discuss about some abelian groups. So abelian groups, if we recall, in the previous module we have already come across this abelian group that is denoted as G, sometimes denoted by G dot. Here dot is an operator which is generic and can refer to addition, multiplication, or some other mathematical operation. It is a set of elements with a binary operation denoted by dot that associates to each ordered pair a comma b of elements in G an element a dot b in G, such that the following axioms are obeyed. A1 is a closure. If A and B belong to G, then A dot B is also in G. Associative is A dot B dot C is equal to A dot B dot C for all A, B, C in G. Identity element is there is an element in E in G such that A dot E is equal to E dot A is equal to A for all A in G. Inverse element, for each A in G there is an element A dash in G such that A dot A dash is equal to A dash dot A is equal to E. Commutative gives A dot B is equal to B dot A for all A, B in G. A number of public key ciphers are based on the use of an abelian group. For example, Diffie-Hellman key exchange involves multiplying pairs of non-zero integers modulo a prime number q. Keys are generated by exponentiation over the group. So with the exponentiation defined as a repeated multiplication, for example, if we consider a power k mod q, then this can be written as a into a number of a's, k number of a's mod q. So to attack Diffie-Hellman, the attacker must determine k given a and a to the power k. This is the discrete logarithm problem. For elliptic curve cryptography, and operation over elliptic curves called addition is used. Multiplication is also defined by repeated addition, like a into k, a plus adding a k times. Where the addition is performed over an elliptic curve, cryptanalysis involves determining k given a and a into k. So an elliptic curve is defined by an equation in two variables with coefficients. For cryptography, the variables and coefficients are restricted to elements in a finite field, which results in the definition of a finite abelian group. Before looking at this, like the elliptic curves in which the variables and coefficients are real numbers, so this case is perhaps easier to visualize. And when it comes to elliptic curves over real numbers, elliptic curves are not ellipses. They are so named because they are described by a cubic equations, like it is similar to those used for calculating the circumference of an ellipse. In general, cubic equations for elliptic curves take the following form, which is known as Weierstrass equation. Y square plus axy plus by is equal to x cube plus cx square plus dx plus e, where a, b, c, d E are real numbers. And for our purpose it is sufficient to limit ourselves to equations of the form, that is y square is equal to x cube plus ax plus b. Such equations are said to be cubic or of degree 3 because the highest exponent they contain is a 3. Also included in the definition of an elliptic curve is a single element denoted O and called the point at infinity or the 0 point, which we discuss here. To plot such a curve, we need to compute y is equal to root of x cube plus ax plus b. So for given values of a and b, the plot consists of positive and negative values of y for each value of x. So thus each curve is symmetric about y is equal to 0. Here the figure shows two examples of elliptic curves. So the formula sometimes it produces a weird looking curves, but let us consider the set of points like e of a comma b consisting of all of the points x y that satisfy this equation together with the element o. So using a different value of the pair a comma b results in a different set e of a comma b. Using this terminology, the two curves in this figure depicts the sets as e of minus 1 comma 0 and e of 1 comma 1 respectively. So this figure shows the example of elliptic curves. So geometric description of addition. So it can be shown that a group can be defined which is based on the set e of a comma b for some specific values of a and b. So that provides the following condition to be met, that is 4a cube plus 27b square, which is not equal to 0. To define the group, we must define an operation called addition and denoted by plus for the set e of ab, where a and b satisfies this equation. So in terms, the rules for addition can be stated as follow. If 3 points on an elliptic curve lie on a straight line, their sum is O. From this definition, we can define the rules of addition over an elliptic curve. Here O serves as the additive identity, thus O is equal to minus O for any point P on the elliptic curve, like P plus O is equal to P. So here we can assume that P is not equal to O and Q is not equal to O. Negative of a point P is the point with the same x coordinate but the negative of the y coordinate, that is if P is equal to xy, then minus P is equal to x comma minus y. These 2 points can be joined by a vertical line, and note that P plus of minus P is equal to O or 0. So to add 2 points P and Q in with different x coordinates, draw a straight line between them and find the third point of intersection R. It is easily seen that there is a unique point R, that is the point of intersection. So which is a tangent to the curve at either P or Q, in which case we take R is equal to P or R is equal to Q. So to form a group structure, we need to define addition on these 3 points. P plus Q is equal to minus R. So we can define that P plus Q to be the mirror image of the third point of intersection. The fourth is the geometric interpretation of this preceding item also applies to 2 points, that is P and minus P within the same x coordinate. The points are joined by a vertical line which can be viewed also intersecting the curve at the infinity point. So we therefore have this P plus of minus P. To double a point Q, draw the tangent line and find the other point of intersection S. Then Q plus Q is equal to 2Q, which is equal to minus S. So with the preceding list of rules, it can be shown that the set E of A comma B is an abelian group. Next is algebraic description of addition. Here we can see some results that enables the calculation of additions over elliptic curves for 2 distinct points, that is P is equal to xp comma yp and Q is equal to xq comma yq, that are not negatives of each other. The slope of the line L that joins them is delta, is equal to yq minus yp divided by xq minus xp. There is exactly one other point where L intersects the elliptic curve, and that is the negative of the sum of p and q. After some algebraic manipulation, we can express the sum as r is equal to p plus q, as xr is equal to delta square minus xp minus xq, and yr is minus yp plus delta of xp minus xr. We also need to be able to add a point to itself, that is p plus p is equal to 2p when yp is not equal to 0. So the expressions can be written as xr and yr. xr is equal to 3x square p plus a by 2yp whole square minus 2xp. Yr can be written as 3xp square plus a by 2yp into xp minus xr minus yp. Next is elliptic curves over zp. So here elliptic curve cryptography makes use of elliptic curves in which the variables and coefficients are all restricted to elements of a finite field. Here the two families of elliptic curves are used in cryptographic applications: prime curves over zp and binary curves which is used in cryptographic applications. So this prime curves are over zp and binary curves over gf of 2 power m for a prime curve over zp. So here we can use a cubic equation in which the variables and coefficients all take on values in the set of integers from 0 through p minus 1, and in which these calculations are performed for modulo p. So for a binary curve defined over gf of 2 power m, the variables and coefficients all take on values in 2 power m, and in calculations are performed over gf of 2 power m. So this points out that prime curves are best for software applications because extended bit fiddling operations needed by binary curves are not required. So for elliptic curves over zp, as with real numbers, we can limit ourselves to equations of the form, but in this case with coefficients and variables, that is limited to zp. Y square mod p is equal to x cube plus ax plus p mod p. Here we can take the values for a, b, x, y and p for the different values. So with all these values we can prove that LHS is equal to RHS. So this is a table which shows the points like other than O on the elliptic curve. This figure shows the points on this elliptic curve. And the rules for addition over EP of a comma b corresponds to the algebraic technique that is described for elliptic curves defined over real numbers. For all points p, q belongs to EP of a comma b. So p plus o is equal to b. If p is equal to xp comma yp, then p plus xp minus yp is equal to 0. The point xp minus yp is the negative of p, which is denoted as minus p. For example, like it can be a e23 of 1 comma 1 for p is equal to 13 comma 7. We have minus p is equal to 13 comma minus 7, but minus 7 mod 23 gives 16. Therefore minus p can be written as 13 comma 16. This is also in e23 of 1 comma 1. If p is equal to xp comma yp and q is equal to xq comma yq, then with p not equal to minus q, then r is equal to p plus q is equal to yp xr comma yr. This is determined by the following rules, that is xr is equal to x square minus xp minus xq mod p. Yr is equal to lambda of xp minus xr minus yp mod p. So here we have all these equations for this rule, elliptic curve cryptography analysis. Coming to this elliptic curves over GFF of 2 power m. So that a finite field GF of 2 power m consists of 2 power m elements together with addition and multiplication operations that can be defined over polynomials. So for elliptic curves over GF of 2 power m, we use a cubic equation in which variables and coefficients all take on values in GF of 2 power m for some number m, and in which calculations are performed using the rules of arithmetic in GF of 2 power m. It turns out that the form of cubic equation appropriate for cryptographic applications for elliptic curves is somewhat different for this GF of 2 power m than for ZP, and the form is y square plus xy is equal to x cube plus ax square plus b. So here we can see that points other than O on the elliptic curves. So this is for different value. So it is understood that the variables x and y and the coefficients a and b are elements of this GF of 2 power m, and that calculations are performed in GF of 2 power m. And considering as an example, let us use the finite field GF of 2 power 4 with the irreducible polynomial f of x is equal to x to the power 4 plus x plus 1. This yields a generator g that satisfies f of g is equal to 0 with a value of g power 4 is equal to g plus 1, or in binary g is equal to 0 0 1 0. We can develop the powers of g as follows, like from g naught to g to the power 15. So for example, here g power 5 is equal to that can be written as g power 4 into g, that is equal to g plus 1 into g is equal to g square plus g as 0 1 1 0. Now consider the elliptic curve y square plus xy is equal to x cube plus g power 4 x square plus 1. In this case, a is written as g power 4 and b is written as g power 0 is equal to 1. One point that satisfies this equation is g to the power 5 g cube, and it is as shown here. So the table lists the points that are part of this e2 power 4 of g power 4 comma 1. This plots the points. This can be shown that a finite abelian group can be defined based on the set e2 power m a comma b, provided that b not equal to 0. The rules for addition can be stated as follows, like for all points p q belongs to e2 power m a comma b, and these are the rules to be followed, the three notations. This is a figure for elliptic curve. So here the fourth one is like if p is equal to xp comma yp, then r is equal to 2p is equal to xr yr. This is determined by the following rules. Xr is equal to lambda square plus lambda plus a, yr is equal to xp square plus lambda plus 1 into xr. So finally we'll get lambda as xp plus yp by xp. Thank you.